Welcome to the fourth class of this short course. Okay, yesterday we saw the basic math behind general relativity. Today we are going to get into physics, proper physics. So it's going to be much more fun today than it was yesterday, but yesterday was necessary. So today we're going to introduce the field equations, Einstein field equations. So the actual meaning of these guys. What does these equations mean actually? So just remembering, yesterday we saw that this guy quantifies the curvature of space-time, and that thing is what we interpret as gravity. Gravity is simply the deviation from the geodesic motion. That's what equivalence principle says actually. And from this guy we can build this guy here. And this guy with the lambda here is just a constant, is the most general secondary order tensor that we can build from this guy. Okay, this guy and the metric, of course. And why secondary order, we'll see in a bit, because we need this guy, and this guy is going to be secondary order tensor. So just remember that the Christoffel symbols, or the connection that we have, we are using this one, which is compatible with the metric. So that's the only connection that's compatible with the metric. So this is the, geometric structure of the theory. We understand the meaning of all of these things. Now we need to understand the meaning of the other side of the equation, because in the one side of the equation we have the measure of local space-time curvature, is a density of curvature, and this guy must be a density of energy, momentum, and everything else. So that's Einstein equation. So we needed to define, these guys define it. It's going to be this one, and this guy we need to build. But how to build this thing? Well, first of all, it must be something that in the limit, in the weak field limit, in the Newtonian limit, this is going to be just the mass, because the mass is the only source of gravity that we have in Newtonian theory. So it must reduce to, it doesn't matter what these guys says. If you're talking about gravity, in a certain limit, it must recover Newtonian gravity, because we know that this works. You can send people to the moon using Newtonian gravity, so it works. So the source of gravity, and the source of gravity is this guy. It must be a density, first of all, because the equations they equate the equation simply equate the densities. So we need the densities in one side. So as easy to build the densities, let us start with the number density. Let us think about, to have a box full of a gas and with any particles inside of it. So we go to the rest reference frame of this guy. This is always possible because it's a massive guy, so we can always find a transformation where we go to the reference frame of this guy, where the system is at rest with respect to us, and then we define the density just like this. V naught is the volume in the rest frame. So in a reference frame moving with us in a certain direction, that's going to be the density of this guy. So because of Lorentz contraction, the density increases. That's a very nice. That is a very nice problem. Regarding to this is a side note. Think about you're in a submarine and you are traveling in the ocean. According to you, the density of the water increases. But according to someone in the water, your density increases. So the question is, you sink or not? That's Archimedes' law. Yeah, the answer was given by a professor in São Paulo, Jorge Matzes, and actually you sink. But you need general relativity to explain this. It's a very nice paper published in Physical Review D. That's related to this change in densities. So we can write this in terms of a 4 velocity vector. This is just the time component of the 4 velocity vector, and this is the 3-dimensional velocity of the guy. So, and then we can simply write the number, the density number 4 vector like this. This is the usual way we define densities, and this is the time. The time component is the density that we just wrote here, and this is the current in the direction of motion. Okay, so we can define it, these four vector in which the time component is a density, and the space component is a current density. Okay, this is usually do this in electrodynamics. You do this in as a simple example like this. But so, in summing up all of these things, we need to build a scalar quantity from this volume, because a density associates something with a volume, with a 3-dimensional volume. Okay, that's what we just did. So in this 3D volume, it lives in a 4-dimensional space. It doesn't matter if it's just space or space-time. It's just space. So in order to do this, we just build this quantity. Okay, with the density. So densities, we conclude densities are fluxes in a time-like direction. We just saw this. This is just a flux in the time-like direction. So it's just a thing that's here and just flowing in the direction of time, but not moving in spaces. So this is a density. And currents are fluxes in space-like directions. So in direction of space, things are moving, particles are moving, we have a current. Okay? So this is the basic thing that we learn about densities and current densities. We did the same thing in electrodynamics. It's exactly the same thing with the electric charge. But here, we need to build a density based on energy and momentum, because we know that energy and momentum are the sources of gravity. Einstein knew did, and so you need to build a density from this guy. But this is not a scalar. Momentum and energy in relativity, they are not scalar functions. They are part of a 4 vector. The 4 vector, the momentum 4 vector. This is the energy density, and this is the momentum of the system. Okay? So we need to build a density from this guy. But to build a density, this guy here, we need a 2-dimensional, 2 indexes object, because you need to contract with the oriented object. You see, this volume can be a space-like or a time-like volume. It doesn't matter. What tells you is this guy with just, is orienting your volume in a given direction. If this guy is time-like, then you have a density. If this guy is space-like, then you have a current density. That's the idea of building this guy, and that's why this guy here has 2 indices. It cannot be 3, it cannot be 1. It must be 2 in order for this equation makes sense. Okay? That's why the energy momentum tensor has 2 indices, and that's why we need 2 indices on the other side of the equation. The Einstein's equation. So this is what we call energy momentum or energy momentum stress tensor, because it also encompasses stress. Let us see how interpreted this guy. What's the meaning of this thing here, and why is it the source of a gravitational field? So we consider the volume, space volume. So the orientation of this guy is just this. Time-like, 0, 0, 0. So it just moves in time, nothing else. And this is a space volume. So that equation that I just showed is, it translates to this because, okay, let's see. I put t here, but the t here is 1. The other one are 0. So just the t component remains. Is that okay for you with the summation, no, of the indexes? Okay. Then you have this equation. But what's the meaning of this equation? Well, these guys runs from t in the coordinates, the space coordinates. The first component is t. T is just, I mean, this is energy density. This is just energy density. Bro, so the 0, 0 component of the energy momentum tensor is just the energy density of the system. Okay? Now, how about the space direction? Well, space direction is just the density momentum. It's the momentum density. There's nothing beyond this. So these guys are sources of the curvature. So let us consider now a time-like surface. Like I just choose these coordinates, y and z and t, to make my three-dimensional volume in space-time. So this guy, do you understand that this guy is orthogonal to this volume? Okay, it's hard to see these, I mean, to visualize these, but if you pick up any vector here, it is going to be perpendicular to this guy, orthogonal to this guy. So that's the meaning of orthogonality, at least here. It's a little bit different for null surfaces, but okay, we'll talk about this later. I just pick up this one. I can pick up any coordinates here. I mean, x and z, x and y, it doesn't matter. It's going to be exactly the same. So the energy momentum tensor, that equation can be written like this. That's the area, this area here, and that's time. Okay, just rewriting the equation. But what happens is that the first component of this guy is just this, which the energy flux in the x direction. But this is nothing but momentum density. So we have energy momentum, the energy momentum tensor. The first component is the energy density, and then we have energy momentum density and momentum density here. And then the last component, the space components of this guy, is just this guy. But this guy is the variation of the momentum over the area, which is a force. So this is a force. This is sorry, it's wrong here. This over this is a force. So this force over the area is pressure. So this is the current, momentum current. Momentum current is exactly the same as pressure. So it's what you call pressure, actually. So here, the space components of this guy, and this holds for A and J. So if I put A and J here, then that's as the momentum current is the pressure is the component of the pressure in the x direction due to the I momentum. Okay, that's the space part of the spatial part of the energy momentum tensor. So that's the meaning of the energy momentum tensor. We have energy density, we have current density with our momentum current, and we have pressures, which are stress. That's all the meaning of the energy momentum tensor. So all of these is a source of gravity. So pressure is also a source of gravity. That's extremely important, actually. In Newtonian physics, just mass is a source of gravity, but here everything is a source of gravity. Everything couples to gravity, and it couples to gravity in exactly the same way. In this way, gravity is, I mean, absolutely universal. It at the most inclusive force interaction we have, because it simply doesn't care who you are, what you are doing. It couples with you in the same exact way. So general relativity. General relativity turns out to be this thing. Einstein postulated this guy. You have the Einstein tensor, which is just this guy. Okay, there is a side note here. When Einstein postulated his equation was exactly like this. So curvature and energy momentum tensor. But then he realized that these thing has no static solution. I mean, there are no solutions of these equations that for the universe that says that the universe is static, is not changing. Okay. At that time, Einstein didn't know that the universe is actually expanding. Nobody knew actually. But in 1925, 25, 25, Hubble discovered that the universe is expanding. But Einstein wanted to correct this thing. He put another term here, which is just a constant times the metric, without the R here. This is a cosmological constant. With this thing, if you fine-tune the cosmological constant, then you are able to find a stable universe, which a stable static universe, which is simply static everywhere. It doesn't expand, it doesn't contract, anything else. But first of all, this was a bad thing because he would be able to predict that the universe wasn't actually expanding. I mean, this would be amazing. But anyway, but this is not the most the worst case, the worst mistake that Einstein did here. The problem is that if you put another one, you have a static solution, but it's highly unstable. Any fluctuation that you have in the distribution of matter and energy here would make the universe or expand or contract. There was no stable solution. So it's impossible. If the universe followed these equations, it's impossible to be static. It's literally impossible. But anyway, that's why we write the equations like this, but a bunch of people use the equation with the cosmological constant, especially people that are working in dark energy and dark matter problems. Okay, we will not use this thing here. But we have two constants here. The first one is lambda that we need to fix, and the second one is this kappa that we need to fix. The first one comes from the conservation law. This guy is the energy and matter content of the universe. So this must be locally conserved, because we know that although global conservation of this thing is a little bit complicated, but locally these things are conserved. Okay, so this means that if I have energy in a given point, and if this thing changes, something must get into or get out of that point. This is just expressed mathematically by the continuity equation, which is this set of equations here. These are all the possible continuity equations we have. So if you do this thing and make the calculations, we know how to compute this guy, we know how to compute this guy, so we know how to compute the derivative of this guy. Because if this is 0, this is also 0, so the covariant derivative of this guy must be 0 by conservation laws. And this implies, if you make the calculation, this implies that lambda must be equal to -1/2. So in order to conserve energy. The other one is a little bit more complicated. You have to take the Newtonian limit, and the Newtonian limit, what you do? You go to extremely weak field, so you write the entire metric here in terms of Minkowski metric plus some correction, and then you study the equations for this correction, and you impose that you have extremely low velocities, extremely low momentum, extremely low energy, and anything like this, and you get up and you end up in for this correction, you end up in an equation just like Newtonian equation for gravity. I mean, the Laplacian of the potential should be equal to be proportional to the mass density. That's the most relevant equation that you get. And from this, for this equation here to be exactly equal to Newtonian equation, this kappa must have this value. There is a c here, but c is equal to 1, so but that is a c, is divided by c here, c to the 4th. So this is the coupling constant. And we end up at the Einstein field equation. So that's the field equation that governs the evolution of the entire universe actually. So that speed of light. Oh, it's relativistic, yeah. So light is everywhere here. Light is, we need. I mean, the causal structure of space-time in the Minkowski space-time, we have light cones everywhere. This light cone is defined. The inclination of that light cone is defined by speed of light. It can be different, it can be, but we don't know. But the value of this quantity is not important. Important that that is a limit. So this is Einstein field equation. This is a very highly complicated equation, and usually this guy depends also on the metric. So we define the Lagrange of the system, and this guy is defined as the variation of the Lagrange with respect to the metric. But if you don't know the metric, you cannot define the energy momentum tensor. So usually you have to solve this equation in both sides at the same time. And this is extremely hard, and that's why you have only a few solutions of this guy. And even numerical simulations of this equation is extremely hard. Oh, this is highly nonlinear because of these. You see here, this is the connection. So if I contract this guy rho with mu, which gets me this guy that appears in Einstein's equation, I just contracting here, but it depends on the derivatives of the connection and products of the connection. But the connection depends on the derivatives and products of the metric. So this is highly nonlinear because these are differential equations for this guy. So you have products of everything. But the main message here, before we enter in actually solving these equations, as I told you, today is going to be very much more pleasant physical thing. So, what did we see up to now? Gravity is not a force because we want to avoid action at the distance. So gravity cannot be a force. Gravity must be described by a field in a way that the interaction between things travels through the field at a finite speed. So we want causality. So, and also, Einstein realized that gravity and space-time is the same thing. I mean, the field that we call gravitational field, is the same thing as we call space-time. And we feel gravity when we deviate from the geodesic motion, from free fall, because the equivalence principle tells us that when you are in free fall, special relativity holds. So when you deviate from free fall, like we are standing here, we are not free falling, so we are feeling gravity. Okay? Something must hold us here. So that's what we understand as gravity today. Is the best description that we have describing this field, which is a very different field from all other fields, because the other fields of nature live on top of this guy because they are defined on top of space-time, and these guys is just there, and it has this strange property. This is the central equation we have in general relativity, which is Einstein field equation. There is a constant here that I always put equal to 1 in the calculations. This is a problem because in the end of the calculations you have to back this thing, and this is a problem. But anyway, um, special relativity. Special relativity, we have no absolute velocity, but relative velocities we have. I mean, special relativity, I can define vectors, and I can change vectors. I can change coordinates of these vectors. They change, but the relative position of these guys don't change under Lorentz transformation. So in special relativity, we can define relative motion. So we do this because I mean relative orientations of vectors in space-time don't change, doesn't change. And we have global inertial frames. We have inertial frames that covers the entire space-time. Okay, that's usually we have there because we don't have gravity there. So gravity, special relativity, and Newtonian space-time are just special instances of general relativity. It's when gravity is zero. That's the content of equivalence principle. When we are free falling, we don't feel gravity because we're just in a geodesic. Of course, except for tidal forces, but this is a different thing. Then these guy hold. That's the equivalence principle. Telling in a different way, in free falling, space is Euclidean. That's another way to state the equivalence principle. If I can measure, I can measure deviations from Euclidean postulates, then I call this gravity. That's what we call gravity, actually. It's how we deviate from Euclidean geometry. And then there is no absolute motion, but there is no relative velocity also. Because of vectors, as we saw, there are no way to cover the entire space-time with a single coordinate system. So we must associate to every point in space-time a vector space. So vectors belong to different points in space-time, events in space-time. They belong to different vector spaces. And to compare these guys, we use parallel transport. Parallel transport depends on the path. So there is no way to define relative motion. There's no meaning. I mean, the question, what's my velocity with respect to that galaxy there? This question is meaningless. It's mathematically meaningless because there is no way to answer this thing. We just need to learn how to live with that. But of course, you say no. But people define the velocity of the galaxies with respect to us. Yeah, but this is not the velocity. This is just a different thing. What happens there is that we assume that let us say the hydrogen atom there emits the same spectrum as here. So we just look at the Doppler effect and associate an effective velocity with that guy. But what really happens is that the galaxy is there. I don't know what's doing. Probably it's not moving actually. And what happens is that the space between them, the metric changes because the universe is expanding. That changes the frequency of the light. So nothing is moving. It's just the space that's stretching. The space-time that's changing. That's what we call Doppler effect in relativistic context. But has nothing to do with the velocity of the galaxy. This is impossible to define. So, any questions here? I mean, that's the basic meaning of general relativity. That's what general relativity really is, actually. Okay. Oh. Obrigado.
So I'm trying to understand this idea of free falling is Euclidean. Like in this kind of description, you will say that you can go to a frame where the free falling is plane in this frame or
No. Look. What I'm saying is that free falling, equivalence principle tells you that in free fall, special relativity holds.
Yeah.
And we know this.
Mm-hmm.
And you know, because in my free falling, if I'm free falling with this thing, it's just we stay here. If I'm not holding, it just stay here. Inertia holds. Inertia, Newton's law of inertia just hold here. And everything looks like if I live in a space in which the laws of special relativity hold. But special relativity is just a theory of space-time.
Mm-hmm.
And this says that space flat. So space respect the Euclidean geometry. So when we're free falling, every measure that you do there to detect the geometry of the space will end up Euclidean. When you deviate from this, then you call this thing gravity. This is not an effect of gravity. This is what we call gravity. So in this sense, the entire job of gravity is to break down Euclideanity. Does this word exist? Okay, but it's to break down the Euclidean character of space. That's the entire job of general relativity. That's why Einstein postulated the equivalence principle when he realized this.
Yeah, no, that makes sense. But if I want to compute, for instance, the curvature on this point of space, for instance, it will be curved because we are in the presence of mass around, because of the Earth.
No, it's not. It's not because of gravity. It's not because of mass. Let us think that we have some gravitational field, like the Earth.
Yeah.
So here I'm detecting curvature.
Yes.
Because things here do not follow geodesics, but we feel this. I mean, we just feel this.
Mm-hmm.
You need a chair to hold you there.
Yeah.
So we are not in an inertial reference frame.
Yes.
When you go orbiting the Earth, then you are just free falling.
Yes, exactly.
Then you feel no gravity. You feel nothing. Gravity for you doesn't exist.
Yeah, but
and the laws of special relativity apply.
yes, I agree. But you don't have a gravitational field when we are orbiting the Earth.
Well, the gravitational field is just a state of the space-time. What you call gravity is when... Look, gravity is not a thing that's acting on you. It's not this. Gravity is, for instance, if I have clocks in satellites, and we do have these, the fact that they tick differently, this is regarding the special relativistic time dilation, just gravity. The fact that they tick differently, and we can detect this, is what you call gravity. It's not an effect of gravity. That's why gravity is, if I'm free falling, I cannot detect gravity. Gravity for me simply doesn't exist. I'm just in the flat space-time. For me, space-time is flat. This is very critical, because if I'm standing here and I'm looking at a black hole, that's in some space-time point. Since I'm standing here, I can see the horizon. Well, I cannot see the horizon. I cannot see the horizon because it's black, but I can see the effects of the horizon. But for a person that's free falling, the horizon doesn't exist because it cannot see the horizon. That's the point. The point is that if you are free falling, you follow geodesic. In geodesic, this guy holds, and you cannot detect gravity. unless for tidal force. I mean, when you deviate from this, you call this what you feel gravity.
Yeah.
It's not an action of gravity. It's just because, I mean, you are not in the geodesic motion.
Okay, so if you want someone is on a satellite around Earth, he will probably understand that space-time there is not flat because actually there are tidal forces.
Oh yeah, if you can measure tidal forces, then it's over. Space-time is not flat.
Okay.
Well, that is no way, because there are no homogeneous gravitational field.
Okay.
Just, I mean, locally homogeneous. So in this sense, inertial reference frames are just, I mean, an abstraction.
Okay.
They don't exist actually, because there will always be tidal forces.
Yeah. No, that's completely. Thank you.
Wow. Of course. Let us think about not space-time, but a positive Riemannian space, Earth. So here, if I want to define vectors here, I need to use the same tool that we use it here, because remember, I can put a vector here, but this is not a vector defined on a manifold. It's a vector defined on a three-dimensional bigger space. We want to do this with just in intrinsically way inside a manifold. So we do this by derivatives, or by the derivatives at curves. So then I define locally here tangent space at P, and then I can define another vector here at Q, and another tangent space here. Okay? Then I want to compare this guy with this guy. But in flat space time, in flat space actually, if I have this guy and this guy here, I want to compare these two. What I do? Well, I just move this guy to here and parallel to itself. And then I came here and I can subtract these guys. If I'm here in special relativity, the same thing holds, because if I change reference frames, these guys change, but the relative orientation between them don't. That doesn't change. So I can do this there. But here, I must do the same thing. I cannot compare this guy with this guy, because simply they belong to different spaces. I cannot do this. Depending on how the motion here and here, we will end up in different relative orientations. So we have infinitely many. Yeah, yeah, yeah. It's not the velocity of things. Let us say that you have a galaxy here. This is supposed to be a galaxy, okay? And we are here. What we do? Well, we know that the basic constituent of this guy is hydrogen. So we just measure the spectrum of the light that hits us here. And we suppose, well, I have a hydrogen atom here, and it has certain characteristic spectrum. So if I measure the light here, I assume that's hydrogen, and I assume that the hydrogen there behaves exactly the same as here. This is an assumption. It's a very good one, but we don't know if it's true. And then we measure the light here, and we compare the spectrum of the hydrogen from the galaxy, and it's going to be different. Then we compare these two things, but we know that to the motion, that's Doppler effect. So Doppler effect, I can put a velocity, and I put the velocity here. So that's the relative velocity that these guys should be moving with respect to me in order to see this changing spectrum. Okay, that's true. But the fact is that these guys not moving. What happens here is the same thing as, think about the balloon. You have a balloon, then you put some point in the balloon, covering the surface of the balloon, and then you start inflating the balloon. The points are not moving. The only thing that's moving is the space between the points, is the balloon that's stretching. The same thing happens here. Light travels at finite speed. So while it's traveling here, the metric here is changing. It depends on time because it's expanding. If the space-time stretches, then this stretches the frequency of these guys. So you have a deviation. And that's the meaning of these guys. It's not a relative velocity of the guy, but it's the way the space-time is stretching, is expanding. That's the meaning of the relative velocity here. It's very strange, these things, because think about the gravitational wave, how they measure gravitational waves. If you have just one point, if you have an magnetic charge and an electromagnetic field passes here, it will react. If you have just a mass and a gravitational wave passes here, nothing happens. Absolutely nothing happens. You need 2 points. And then the gravitational wave passes here. What happens is that if a gravitational wave passes here, what happens is that me and Naim will just make this in this direction, and the other direction will be contracted. But none of us will feel anything. There'll be no forces. It's just the space between us that's changing. Nothing's happening with us, actually, because there is no force. There is no gravitational force here. So that's the way they measure these things. That's why they needed an interferometer to measure these things, because they measure the relative displacement between two things, two mirrors, and then you have the change in the fringe visibility. So that's general relativity. That's the way it is. It's extremely. That's why I told you at the beginning that this is, for me, is the most difficult theory we have in physics. I mean, to understand these things is extremely hard. It's not. I mean, the physical implications of these things is very, very hard. Let us try to understand a little bit more. Let us think that we have in a very small region of space. There is a very good paper by this guy, John Bias. It's an excellent researcher, by the way. This guy is amazing. He published in American Journal of Physics a paper that's called The Meaning of Relativity. I don't know if it's the meaning of relativity or the meaning of Einstein's equation, but one of these, in the American Journal of Physics. Excellent, this paper. He tries to understand, he tries to explain the meaning of Einstein's equation. So think about a small sphere, and this must be small, full of massive dots at rest in a given reference frame, as measured by the dot in the center. Okay, so we have a ball with particles, non-interacting particles, just with gravity. And we have in the center, we put the reference frame in which all of them are at rest at a given instant of time. Okay, measured with respect to this guy. And then you write Einstein's equations in this thing in first order. What happens is that, believe me, it's possible to prove. If anyone wants to discuss the details of these things, just knock on my door. That it's going to be a pleasure to derive this equation. I'll not put it here because it needs to introduce something more than we did, like geodesic deviation equation and things like this. Otherwise, we cannot derive this thing, because the geodesics, these we solve, the geodesic parallel transport is on velocity vector. So since all of these particles are only interacting with gravity, all of them follow geodesics. This is the basic thing that we saw in the very beginning. If you have no forces applying on you, you follow geodesic. There is no other way. So the only force that's being applied on me now is the one by the Earth that's keeping me here. There is no gravitational force on me. It's just the Earth that the ground that is avoiding me to free fall. So you follow geodesics. Gravity is this a deviation of this guy, and what the guy computes is this. I mean, how these things, how the volume changes because of tidal forces and gravity at all. And then you write Einstein's equations in this specific reference frame, where the particles started at rest, and you go just in first order in time, just the first order approximation, you get Einstein's equation like this. This is the same thing as Einstein's equation. So the second derivative of the volume of this ball divided by the volume computed at that point where the ball was at rest is given by this, the equation. This is the density, and this is the pressure in the three directions. Okay? So if this is positive, this is positive, this is positive, this is positive, what this equation say that the volume shrinks. So gravity attracts. That's the meaning of Einstein's equation. So the geodesics converge. But actually the attracts in one direction, compress in the other one. So that's, but you see that pressure is here as a source of gravity. But then you say, well, why not use this equation instead of Einstein's equation, extremely complicated one? Well, because this is not the entire content of gravity. This is the meaning of Einstein's equation in a single reference frame where we started with the ball at rest. So the full content of general relativity, you have to write this equation in every reference frame with every possible velocities, with infinitely many. So it's much easier to do this with Einstein's equation. So that's and from here you can derive several results just from this equation. It's so I recommend to read this paper by John. It's really, really amazing. Yeah, it's possible to do. No, for Einstein's equation. It's possible to do, but you need well, you define geodesics, and then this comes from the geodesic deviation equation, with gravity. Uh, no. If you have just one particle, there is no gravity. There's no gravity at all. I mean, everything in gravity is relative to something. Let us think about the two black holes free falling each other. So they're in free fall. But free fall is, I mean, you are not accelerating, you're just free falling. Special relativity holds there. So how this can emit gravitational waves? The problem is that for us, they look like they are accelerating. So they must emit. Everything is relative. There are no absolute nothing. The black hole, black hole is a little bit different because you have event horizons and things like this. But usually you are comparing observers, different observers. For instance, me that I'm standing outside the black hole, and a guy that's free falling in the black hole. These guys following a geodesic, but I'm not because I'm standing. So I must see gravity. but the guy doesn't see gravity. So that's that that has huge implications. For instance, to define Hawking radiation. Hawking radiation is defined at infinity distance from the black hole. Otherwise, you cannot define particles because particles are defined through killing vector field. So we needed to define the future direction of time. And when space-time is too curved, you cannot define these things. So particle makes no sense. But for a free-falling guy, it does. But a free-falling guy cannot see Hawking radiation because, I mean, there is no event horizon for him. The singularity is a different thing. Singularity is much worse. Yeah, it's what you call gravity. You're not feeling gravity. It's just you call these gravity. Yeah, you call this feeling gravity. I don't think I understood your question. Okay, okay. We are in one now. But am I interacting with some other thing or just gravity? Just gravity. I mean, just living there. Okay. Oh, it's not sudden, but I mean, it changed in a causal way. But no, no. I mean, I will keep going in a geodesk. The geodesk can change, but I don't feel this. I mean, I'm just in a geodesk. I'm just free falling. That's why you always need two things to define something. You cannot define it with one particle that nothing happens. Absolutely nothing happens. You need at least two. So, just 3 months after Einstein published his paper, Carl Schwarzschild, he was in the war actually, in the battlefield, and he solved the Einstein's equation in the battlefield. These, I mean, Russian guys are really crazy. I mean, but the first solution was this. Of course, the basic thing: static, spherically symmetric distribution of matter. A star does not spin. Just this. There is no such a thing, but no. That's the first solution. That Einstein's equation. So, since you are in vacuum state, we are solving the Einstein's equation outside the matter distribution. So in vacuum. Just, I mean, the Einstein's equation just reduced like this because this happens. Okay, this is the Einstein's equation. So how do we solve this equation? In this way, it's easy because it's highly symmetric situation. So the first thing that he did was to say, look, the metric, the most general form of the metric must be this one. Why? Well, because we have a clear symmetry that if it's static, nothing depends on time, so the metric cannot depend on time. Okay? The other thing, it's static, so time have symmetry must hold. So we cannot have, because the general form of the metric is this, no? Where these are the coordinates, so we should have x and t, y and t, and things like this. But if I have these things, then time have symmetry would be broken, and so we cannot have these terms in the metric. And spherical symmetry demands demands this, and demands that these guys should depend only on the absolute value of the coordinate. So this is just spherical coordinates are arbitrary ones. These are not distances. These are not anything physical. It's just labels that we put there. So this is the most general form that we have in a metric, given the symmetries that we imposed in the problem. Okay? Do you agree? Everybody agrees with this? I mean, we cannot have any other term here. Any other term that you put here that is contained here will break down one of the assumptions. So it's a different solution. Okay? So once I have these, it's easy to proceed because we just need to find these guys, and these guys are positive functions. They cannot change sign. Otherwise, you change the signature of the metric, and this it cannot happen. Okay. So they are positive functions. So the first thing we do, we compute the connection. Because we have the metric, we just put the metric in the connection. The connections are written in terms of derivatives of the metric, so we can compute all the coefficients of the connection. Once you have the connection, we can compute the heat tensor. So we compute all the components of the heat tensor with their functions only of the connection. And then we have these guys will we put it here, Einstein's equation, and these guys will end up at differential equations for A and B, which can be solved, and then we find A and B, we find the metric. Okay, that's the procedure we do, and we start in, these are the non-vanishing components of the connection. We have 64 components here because it's four for each one of the index, so we have a bunch of them, but only these are non-vanishing, and it's symmetric and things like this. Okay, using spherical coordinates. And then we compute the heat tensor. The components of the heat tensor are just this, the non-vanishing ones. This prime here is just a derivative with respect to the r component, the r coordinate. So this looks like, I mean, a very bad set of equations, but no, they are extremely easy to solve. And the solution is just this. And the first thing that happens is that this guy here is a constant, because you are integrating differential equations, a constant should appear there. And this quantity appears. And when we take the Newtonian limit, because this must, I mean, be like the gravitational field generated by spherical mass. So Newtonian limit should play the role here. We need if the mass is small and things like this, we need to recover Newton. And then this implies that this constant should be equal to this guy. Okay, and we interpreted this m here as the mass of the distribution. But in general, we cannot find the mass of the distribution. This is not defined at all. It's a huge problem that you have today, still today, is defining the mass of things. We have several proposals. One of them is the Komar mass and Komar angular momentum, but they're defined at infinite and things like this. It's strange, but anyway, this is a problem. We don't know how to define the mass of things. What we understand by mass. But here in this situation, we interpreted this as mass because of the Newtonian limit. Okay, so we call this mass. And this is the metric, that's Schwarzschild metric. So we see here that when r goes to 0, these metrics diverge. You have a divergence here, you have divergence here. Okay? And this is a problem because the metric is singular here. This is what you call singularity. And Roger Penrose won a Nobel Prize in physics because he proved that the singularities are actually a very common feature of Einstein solutions. We have singularities everywhere. So he proved a set of theorems that are known today as singularity theorems that that explained the behavior of this thing. And he just he conjectured that there are no naked singularities, which means that all every singularity that we have in the universe must be protected by an event horizon. Okay, I will not discuss what event horizon is because it's a delicate issue, but it's something that protects us from violating causality because of the singularity. If there are naked singularities, then we could violate causality. But we don't believe that there are singularities in the world because I mean it's a pointing where space-time simply don't exist. Everything is infinite there. So we don't believe this. Maybe quantum corrections will avoid these sort of things. It can be big, but infinite is too much. And there is another singularity. When this guy is equal to this guy, when R is equal to Rs, then we have another singularity of this guy because this guy diverges. Okay? But this second singularity is not a true singularity. It's just a breakdown of the coordinate system. You can make a coordinate change and you simply get rid of this guy. But this guy you cannot get rid of. And how we know this? Because we know how to compute scalar quantities. And one of the scalar quantities that you can compute is this. Can you see green? Okay. One of the scalar quantities that you can compute is this guy. But what happens is that with this metric, this is equal to 0. Because as I told you in the beginning, this is a measure of the average curvature of the space in every direction. But here we have spherical symmetry, so 0. But there is another one, which is this guy. What happens is that this is this guy. So nothing happens when R, nothing special happens when R reaches this guy. But we still have a divergence when R goes to 0. But I mean, we know that the divergence of this kind appears everywhere, like electrodynamics. If we're computing the electric field of a charged particle, when I go to 0, it diverges. And this sort of divergence appears everywhere. I mean, the fact is that we don't know how to deal with these things yet. But the problem is that this singularity here at R goes to 0, it's what we call true singularity. This is just a breakdown of the singularity, but it has a very special meaning. If everybody, all the mass goes inside this guy is the event horizon. So when you study geodesics of this guy, you see that once you cross this line, it's over. The only fate that you have is the central singularity of things. Let us see how. Of course, I'll not discuss the details of black holes, but just for you to give you an idea, let us see T, and here the coordinate R, these coordinates. And then let us think about, we have a spherical distribution of mass that's just collapsing under gravity. Okay, so in one dimension, this goes this, and collapsing means this. Okay, it's just collapsing the radius. This way, the coordinate radius is decreasing. But at certain point, this is the singularity. So at certain point, something happens, and what happens is that this is the event horizon. It protects the singularity, but protects against what? Against us, because here is flat space-time. We are far away, infinity. So these are light cones. All of them are here. This is flat space-time. So that's the causal structure here. But what happens when we get closer to this guy? When it gets close to this guy, what happens is that this guy starts to deform. And at a certain point, you cross this guy. And this line is exactly on the event horizon because the event horizon is a null surface. Which means that the distance between any 2 points on this surface is 0. But what happens here? What happens here is that if you are falling down here, once you cross this line, your future is the singularity. For you, there is no singularity yet, because the singularity is in your future. You are just falling. At some point, you find it. But singularity is not, in this sense, singularity is not a place in space, but is a moment in time. So that's the causal structure of a black hole, a very simple black hole. And there is no way. Once you enter here, it's over. You can. The only thing that you can do is to go through the singularity. If the guy is rotating, then is a like Kerr solution. Kerr solution, the light conic does the same thing, but it also flips in the other way. So you have to go to the singularity, but you cannot stand still. You have to rotate also. There is no other way. You cannot stay standing there because the space-time doesn't allow you to do this. So it's the basic idea of black hole, very simple one, and this happens. The fact that there will be event horizons here is a conjecture that's called there is no naked singularity, and conjectured by Roger Penrose. Why it would violate causality is a different thing. We need to understand Penrose diagrams and then some other things to explain this. But so that's these sort of things we can understand geodesics, we can understand the deflection of light when passing through the sun, we can understand the derivation of Mercury's perihelion and everything like this. So this was the first solution derived by Einstein, but by Karl Schwarzschild, just 3 months after Einstein published his paper, his theory. Outside mass distribution. Yeah. Yeah. For the sun, this is inside the mass distribution. That's why the sun is not a black hole. It's that very inside. Also the Earth. The Earth, this guy is I don't remember exactly the name, but it's a few centimeters. For the sun is I don't know, a few kilometers or something like this. It's different. It's the same thing as you are computing the gravitational field, Newtonian gravitational field, outside a mass distribution, inside the mass distribution. They're different. Yeah, the problem is that this guy, once all of the mass goes here, like here, the event horizon starts forming, and then starts increasing, and once it's formed, it's over. And this guy, only light can walk here because it's a null surface that you see. So light can be trapped there. And and actually the way to define these event horizon is how null geodesics behave at infinity. If this is the region where from where no null geodesic can reach the infinity. That's the definition of formal definition of event horizon, which is different from the horizon of the black hole. The horizon of the black hole is defined here. The event horizon is defined at infinity. The fact that these in this particular solution, these guys coincide. Well, yes. I mean, you study the collapse of matter, and you do this numerically, but this is just uh, a, a set of particles that are not interacting with each other, and no quantum effects are being taken into account here. So we don't expect this to hold in general, because I mean, once matter is collapsing, quantum effects will become more important, increasingly more important, and these will make things different. So we don't expect these things. So this is just an abstract um, idealization of black hole. But we know there are event horizons. We don't know what's inside event horizons, but we know that there'll be something different from this, because once matter is collapsing, the assumption that's not interacting doesn't hold anymore, and the assumption that's classical is even worse, because I mean, quantum effects should take place. We have neutron stars that are holding together because of quantum effects. Singular. The, I don't know if I understand what we're actually saying. What do we mean by singular surface? Oh, it's because from certain density that you have here, if you compute, how do we build these things? We have the solution, and then we compute new geodesics. So we compute new geodesics everywhere. We know that new geodesics here follow this pattern, and new geodesics here follow these patterns. So new geodesics generated here, we just follow this. And here they can go out to infinity. That's the way we define surfaces. The surface is the point from every new geodesic generated after this guy. We reach infinity. From this point on, you cannot. Oh, here inside? Oh, it's start being formed. It's just, I mean, starting formed. There is no singularity here. The singularity is not there yet. It's just the matter is collapsing. This is inside the matter distribution. It just starts increasing. It's a dynamical thing. Yeah, it does like this according to general relativity. But we know that's not like this, because we are not taking in quantum effects into account. So there will be difference here. And why we don't take quantum effects into account? Because we simply don't know how to do this. I mean, you don't have a quantum theory of gravity, so we don't know how to compute these things. But we know that it will be important. For this, there are black holes that are eternal. They always exist, like Kerr black hole. They exist since forever, and they will exist forever. We know that this is not possible because the universe is finite. So there's just idealization that makes us understand a little bit about general relativity and how these things behave. And I mean, and to look for a better theory. But we know that this thing doesn't exist in reality. There are black holes, but we actually don't know how to describe them in the full theory. We know they're there because well, we actually have pictures of these guys. And the gravitational waves that we detected at LIGO came from black holes. So we know that they do exist, but we don't know how they are. It's not like this, but this just gives you an idea. Interesting thing here is that if you are outside the distribution, it simply doesn't matter. It's the same thing if you have a black hole or if you have a star. It's this field. So outside the black hole, inside we don't know what happens, but outside the black hole is going to be the same thing. So if you go too close to the sun, the gravitational field is extremely, extremely strong because of this. It doesn't matter if the sun became a black hole or not. It simply doesn't matter. I mean, the gravitational field outside the distribution is given by this. So if you are close to the sun and you pick up the sun and put a black hole in the place, you're going to feel the same thing. Of course, there will be consequences because we need sunlight, but apart just talking about gravity, nothing changes. But inside is a different thing. And we have black holes with two horizons. We have black holes in the second horizon is supposed to be a warm hole to a white hole. So you get into a first event horizon and get out the black hole, but in another universe. There are solutions of Einstein's equation that permit allows this. This is not a breakdown of causality. You can escape the event horizon because you escape the event horizon in another universe. So it's connected part of the universe. Nothing changes. There are plenty of solutions of this key. This is the simplest one where you can understand the basic things of black hole. This one we're gonna use tomorrow. Okay. This is a little bit more difficult to derive because we need a theorem. But the idea is very simple. It's the cosmological solution of the universe. We just say that the space-time distribution of matter is homogeneous. The space-time is homogeneous and isotropic. This means that in every place that there were I be in the universe, I'm going to look the distribution of matter and things, and they're going to be the same in every point of the universe. So it's like I dare and see a distribution of dust, or they call dust or radiation. Everything everywhere is the same. And isotropy, every direction that I look in space is the same. So those are assumptions. If I do these assumptions, what are the most general? What's the most general form of the metric? We have three. That is a theorem that says that this guy is must be one, and this guy must be just because of these assumptions. I can only have a function that depends on time here, multiplying the spatial part, and the spatial part of the metric must have only three. Can have only three geometries, or it's flat when k equals 0, or the universe is closed, which means that it will expand and then contract, or the universe expands forever. It's an open universe with hyperbola. Okay, that's just there are no other possibilities. That's made by making these assumptions. I can only have these three geometries. Always, we're extending along. I'm almost finishing, guys. So the thing that we needed to find is this guy with the scale factor of the universe, and this is written for a very special class of observables, the ones that are co-moving, which means that I don't care about the motions of the galaxy. The galaxies and everything else are just at rest with respect to me. The universe is spinning. We are a very good approximation of these things, of this sort of observables. So these are the co-moving observables of the universe. A different class of observables will be a different. We will see a different thing. So these are co-moving coordinates, and the matter is just modeled as a perfect fluid. So this is the force velocity of the particles. That is the pressure, energy density, and that's the energy momentum tensor of a perfect fluid. Okay, we do this in general relativity. This is measured by in this co-moving frame. This force velocity here, everything is moving in this stance. Well, but these equations turn out to be a little bit more complicated than the Schwarzschild solution. But the way we solve it is exactly the same. We compute the connection, the heat tensor, the Einstein tensor, and the Einstein field equation. But now the Einstein field equation has both sides. But it's exactly the same thing. Once you do this, you get what we call Friedmann equations. So these are the set of Friedmann equations, and this is the conservation law, local conservation law of energy density. And once you put the value of k here, you have the three possibilities of the universe, which will expand forever, the one that is flat, and the one that is as closed. It will collapse. Okay. And the only thing that matters here is the scale factor of the universe, as measured by this co-moving guy. Okay. And so you just solve these dynamics, and you see the universe is expanding. Is an amazing thing, because we started here. That's the prediction of the thing in a single point, and then we go to infinity. But now we understand that it's even worse. We understand that the universe is expanding, but accelerating. The expansion is accelerating. What does this mean for us? Look, just one of the consequences of this guy that is really, really, really nice. Think about we are here. This is our light cone. So once you look to the stars, we're looking here. We're looking to the past, because we are seeing the light that is hitting us was emitted many years ago. Okay, so because of finite speed, traveling speed. So that is an horizon here. From that point on, we cannot see because the space is expanding faster than the speed of light. So the light cannot reach us. And if this guy is expanding, okay, this guy is there, that is this horizon. But if it's accelerating, this horizon is getting closer to us. So the part that we see in the universe is contracting. As time goes on, we have access to smaller and smaller portions of the universe, simply because the space is stretching, the space-time is expanding faster than the speed of light. And light cannot travel faster than light. Nothing can travel faster than light with respect to the space-time. But space-time can do whatever. Space-time simply doesn't care about this. It expands and that's it. So that's what happened today. We are in accelerated expansion of the universe. And people from dark matter and things like this are trying to explain why this is happening. I think we discovered this in the 90s. Yeah, I think in the 90s we discovered that we are expanding, accelerating, expanding the universe. So that's what's happening now, and that's the prediction of general relativity. Except for this part here, the rest is pretty much okay. But this part, of course, here we expect quantum effects to play a dominant role, and we simply don't know what happens here. We simply don't know this thing. But here is Planck scale. And that's it, guys. Thank you. Of course, if anyone wants to discuss the details of these things, it's going to be my pleasure. Yeah, 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 bouncing universe. Well, in the simple model, no, but we can put radiation there, and we can predict the expansion. Well, it is expanding. It's not accelerating. Yeah, yeah, yeah. Dark matter. You need to put extra things because Einstein's equation gives you this. Yeah, Einstein's equation gives you this. You are expanding. Yeah. As far as far as I know, we need to put these thing there, and they're trying to relate to this thing with dark matter, dark energy, all these things. But I never actually worked with these things, so I'm not a specialist. Uh, but as far as I know, you needed to put this extra thing, otherwise you cannot explain accelerated expansion. I don't know if you change the energy momentum, you can get something of this. I really don't know. There are people that claim that, and people I'm saying that Bill Muro and Robert Wald and things like guys like this. I mean, gods of general relativity. They claim that you don't need dark matter, but, but to explain expansion, to explain the rotation curve of the galaxies, that general relativity cannot explain. At least I don't know a calculation that explain. But they claim that you don't need dark matter, dark energy. But I don't understand the arguments. But I mean, people are fighting against this. The thing is that nobody knows, and you have very good people from both sides, and they are trying to argue with each other to try to understand what the theory is going to be. But we know that general relativity must be modified in certain sense because, like quantum mechanics, I mean, both cannot be wrong because they clash. So we need to modify something. And general relativity predicts singularities, which we don't like. So probably both of them will have to change. But yeah, cosmological constant they are studying since ever, and very good people. For instance, the first guy that tried to make a physical, to give a physical intuition behind cosmological constant was Steven Weinberg. Steven Weinberg computed, so no, this is because of the universe is full of fields, quantum fields, and the vacuum of quantum fields fluctuates, and these have energy. So the 0 point energy of quantum fields will give rise to the cosmological constant. The problem is that when Weinberg computed this thing, the order of magnitude because we cannot change Einstein's equation. If you change Einstein's equation, everything falls apart. So if you put a cosmological constant there, this must be very small. Um, so the order of magnitude is 120 different from what could be. So it's not this case. It's, I mean, people are trying to make sense of this thing since ever, and I think that people that work in dark energy and string theory and things like this, they like this constant. At least a colleague of mine there that works in string theory and holography, he likes this cosmological constant. But for falling. Yeah, yeah. It should radiate, but radiate what? Charted particle. Okay, okay, okay. Exactly. It doesn't. It doesn't. It doesn't radiate actually. Um, if I'm just free falling here, and this is charted, I'm free falling with this guy, it cannot radiate. But for a guy that's outside, it must radiate. But look, if I'm standing here and not a free falling, and I'm just holding this guy here, it is accelerating. So it should radiate. This is a very important problem that also was solved by George Matzes in another paper published in Physical Review D by George Matzes and Daniel Vanzella. They solved this problem. You need quantum mechanics. It's a very nice solution. The particle doesn't radiate. I mean, everything is consistent. It should radiate. Yep, but it does. It doesn't, of course. I mean, we know that standing charged particles here do not radiate, and actually it does. It's the same thing as the submarine navigating. It should sink or not, depending on the observer, but actually sinks because of gravity. So these are two papers by George Matzes. He solved these two problems. Oh, thank you. Yeah, tomorrow we're going to see the relativistic thermodynamics. All of these was introduced this thing. Thank you, guys.